Hi everyone. So welcome to the video. I'm going to go over some practice problems for chapter 9, but I do want to let you know about the disclaimer first, okay? So please read the disclaimer on Brightspace, but the gist of the disclaimer is this exam review was not prepared by your lecture instructor. This exam review was prepared by Jesse and I. So we made the exam review. I'm going to make this video. This is Colin. I'm going to make this video, but the faculty instructors have not seen this, okay? I also don't go to class. Jesse doesn't go to class. I don't see what examples they go over in class. I do see the homework and things like that, so I have a general idea of what you guys cover, but I don't see the exact examples. I don't know what they focus on. So don't use this as your only way to prepare. Make sure you're doing the homework. Make sure you're going over your class notes. Don't think that these are going to be the same problems that are going to be on the test. So with that disclaimer out of the way, which is again is also available on Brightspace under this where you found this video, I'm going to go ahead and get started with the first problem. All right, so the first question says the atmospheric pressure is 0.941 atmospheres. What is the pressure in torr? So we're looking at this one right here. So we need to remember that 1 atmosphere is 760 torr, after Torricelli, the guy who invented the barometer. This is basically a millimeter of mercury. So if you have a barometer on a perfect 1 atmosphere pressure day, the gas molecules pushing into the barometer will push the mercury and cause it to rise by 760 millimeters, 2.5 feet, something like that. Probably a little less than that. So that is basically what you need to remember. So in this case, 0.941 atmospheres on the top times, we want atmospheres to cancel out, so we put the 1 atmosphere on the bottom and the 760 torr on the top, and we're again using dimensional analysis like we have done lots of times before. And when you do this math, you get 715 torr, which is choice letter B. All right, so question 2 says, to what volume will a sample of gas expand if it is heated from 50 degrees C to 2.33 liters to 500 degrees C? So in this case, we're relating the temperature and the volume. We're assuming that the moles of the gas inside the container is constant. We're also assuming the external pressure is constant. So we're not going to use the ideal gas law here. We're actually going to use Charles' law, which relates temperature and volume. Now, you can remember Charles' law as if you take a balloon and you heat it up, the balloon will get bigger. So as the temperature increases, the volume also increases. So there's a direct proportionality. Or if you look at the ideal gas law, PV equals nRT, variables that are on opposite sides of the ideal gas law, volume and temperature in this case, are going to be directly proportional to each other. And said another way, for these two sides to be equal, if this one goes up, this also has to go up for them to still be equal, so they're direct proportionality. Now, Charles' law, written individually and not in the presence of the other variables that are constants in this case, is going to be V1 over T1 equals V2 over T2. So these, or this, is how you write a direct proportionality, and this one happens to be called Charles' law. Okay, so now let's look at it. And the other thing you need to remember is that temperatures in Celsius are not proportional. You need to use the absolute temperature in order for it to be proportional. So instead of using 50, you need to add 273 or 273.15 to that, which in this case is 323.15 K. And instead of 500, you need to add 273.15 to that one as well, and you get 773.15 K. These temperatures are proportional to each other. So if you look, 50 to 500 is a 10 times increase in temperature, so you would expect a 10 times increase in volume, except these are not proportional. So you have to convert them to Kelvin, because this temperature is not 10 times greater than this one, right? We're not heating it to 3,200 degrees. We're heating it only to 773 degrees, which is still quite hot, but it's certainly not 10 times this one. So now we can plug in. So in this case, 2.33 liters is to 323.15 K, as some number of liters, V2, that's what I'm looking for, is to 273.15 K. So now you want to cross multiply. So this times this, cross multiply these two, and then you're going to divide by this one. So this times this divided by this. And when you do that math, you find that V2 is equal to 5.57 or 58 liters, which is very close. Note that sometimes you're going to get differences in the last decimal point with these types of things, because some people are going to use 273 and some people are going to use 273.15. You'll note that if you use what am I doing? 273, that's 3 sig figs. That's 5 sig figs. That's the only difference, okay? So you might get slightly different answers in the very last decimal place. Don't worry about that. There's no other answer that's anywhere close to 5.57 or 5.58. So that is basically how you do this one. All right, it says a gas occupies 4.23 liters at 2.25 atmospheres. What is its volume at 3.46 atmospheres? In this case, we can assume that the moles of gas in the container are constant. We can also assume that the external temperature is also constant. So we're relating the volume and the pressure. If you go back to, as I mentioned in the previous problem, PV equals nRT, if variables are on opposite sides, you remember in the last question we did V and T, they're directly proportional. In this case, they're on the same side. We're relating pressure and volume, and this is all basically, not basically, this is all a constant because the moles don't change and the temperature doesn't change. So we're just relating these two variables. If they're on the same side, they're inversely proportional. So if the pressure goes up, if you take a balloon and you put it in a high pressure environment, the volume will go down. Said another way, for P times V to be a constant, you got, if this one goes up, this one has to go down. Well, how do you write that as an equation? It is P1 V1 equals P2 V2, which you may have not need to listen to anything I just said, and just remembered this as Boyle's law. Okay, that's another way of doing it, is knowing the gas law. In this case, you don't need to change the units. Okay, you can have milliliters or liters, it doesn't matter because they're proportional. You could have atmospheres or you could have torr. Again, it doesn't matter because they're proportional. When you have temperature, Celsius temperatures are not proportional to Kelvin temperatures, so you have to change to Kelvin. All right, in this case, P1 I'm going to call as 2.25 atmospheres, and that has a volume of 4.23 liters. P2 is your 3.46 atmospheres, and the volume of it when you increase the pressure is V2, and that's what we're trying to figure out in this problem. So to solve this, we multiply these two and then divide by that one, and we get V2 is equal to 2.75 liters, which is choice letter E. It says what pressure in atmospheres will 0.44 moles of carbon dioxide exert in a 2.6 liter container at 25 degrees C. So we've shown the ideal gas law in the previous two questions, but here we actually need to use it. So PV equals nRT. The pressure, or P is the pressure, has to be in atmospheres, not in torr. V is the volume, has to be in liters. N is the number of moles, moles is a unit. R is 0.08206 or 0.0821 if you have the 3 sig fig version. This is the 4 sig fig version. But what's important is it's liter atmospheres over mole K. And why is this important? Liters, liters, atmospheres, moles, and the temperature has to be in Kelvin. So it tells you the units of all the other things. So in this case, we need to know the pressure. So PV equals nRT. You can plug in and do the algebra, or you can do the algebra and plug in, doesn't matter. I'm going to divide both sides by V. P equals nRT over V. Now, I'm going to plug in. N is 0.44 moles. R is 0.08206. That's liter atmospheres per mole K. I'm not going to write it because I'm not going to have enough space. Okay. The temperature, the T, can't be 25. You have to add 273.15 to that, which is 298.15 K. Note that if you just add 273, you're going to get basically the same answer. It's just the 3 sig fig version if you had 273. It's the 5 sig fig version if you had 273.15. Then the V is going to be 2.6 liters. Okay, so we just plug in, multiply, 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 divide, and when you do that all out, you get that the pressure is equal to 4.1 atmospheres, which in this case is choice letter C. All right, it says which of the following samples will have the greatest volume at STP? Remember that STP is standard temperature and pressure. The standard temperature is 273 K or 0 degrees C, and the standard pressure is 1 atmosphere. And at STP, 1 mole of any gas is 22.4 liters in volume at STP for any gas. Now you'll notice we have 22 grams of helium, 22 grams of carbon monoxide, 22 grams of oxygen, and 22 grams of chlorine. And we're asked which one has the greatest volume. Well, we know that they have a constant temperature and pressure because it's standard temperature and pressure, and we know that 1 mole of any gas is 22.4 liters. Now you'll notice here we have 22 grams of each of these things. This reminds me of the old thing where people will say, what weighs more, a pound of brick or a pound of feathers? Well, a pound of bricks or a pound of feathers have the same weight, right? They each have a weight of 1 pound. In this case, we use masses instead of weights, but it's basically the same idea. But what is there more of, bricks or feathers? A pound of bricks probably isn't even 1 whole brick. A pound of feathers is a lot of feathers, so there's more feathers. For gases, it matters how many molecules there are. It does not matter what their weight is. So if you remember back to your ideal gas law, it's PV equals nRT, where the amount term is N, the number of moles. Well, which one of these is going to have the greatest number of moles? A is going to have by far the greatest number of moles. You don't need to actually calculate it because you know that helium is the second lightest element. The only lighter element is H2 hydrogen. All other, in this case, elements or compounds are going to have a greater molar mass than helium. So since each helium is individually lighter, 22 grams of helium is going to be far more moles than any of these other things. Specifically, this is going to be multiple moles, about 5.5 moles of helium, and it's going to be less than 1 mole of oxygen. So this is by far going to have the greatest volume because it has the greatest number of moles. But you could do the math or you could just look at it. You don't really need to do the math. All right, number 6 says, which of the following will increase the pressure on a gas in a container? So if we go back to our ideal gas law, PV equals nRT, remember, things that are on opposite sides are directly proportional. Things that are on the same side are inversely proportional. Said another way, if you want to increase the pressure of a gas, you either need to increase the number of moles in the container or increase the temperature. Why? Because pressure is directly proportional with the moles of gas and directly proportional with the temperature. So therefore, if you want to increase this, you have to increase one of these two things. How about volume? If you want to increase the pressure on a gas, you need to decrease the volume. So this is inversely proportional. So if you want to increase the pressure, decreasing the temperature will also decrease the pressure. That's not going to work. If you want to increase the pressure, you can decrease the volume of the container. That's what's going to work. And you can't decrease the number of moles. Another way of thinking about this is if you have a container that's this big, all right, and you have some number of moles of gas hitting the walls of this container and exerting a force, and that force, when they hit the walls of the container, is going to be the pressure. And you take it and you force that same amount of gas into a smaller space. Said another way, you decrease the volume of the container. When you decrease the volume of the container, those molecules of gas are going to randomly hit the walls more often because there's less space for them to go to hit the walls. They're more crunched in there, and therefore they're more likely to hit the walls of the container. When they do that, they're going to exert a greater force because they're hitting more often. When they hit more often and exert a greater force, you increase the pressure. So going from a container this size to a container this size, let's assume we can, somehow like squish in this container. We have some device that will squish this size container into this size container without changing the gas inside. The gas molecules are going to hit the walls of the container more often and increase the pressure. Okay. You could also commonly do this if you have a syringe. Okay. So if you have like some kind of syringe, I'm going to try to draw a syringe, which is not going to be good, but some kind of syringe like this, okay, not with a needle, with a blunt end, and you take a plunger, right? If you put your finger on this part of the syringe and you push the plunger down, the pressure increases. Okay, so if you block this and push the plunger down, the pressure increases. Why does that happen? Because you make the volume smaller, and when you make the volume smaller, there's more molecules hitting the walls of the container, exerting a force. All right, this is a hard problem. It says a 0.334 gram sample of an unknown halogen occupies 109 milliliters at 398 K and 1.41 atmospheres. What is the identity of the halogen? So this seems like an unsolvable problem, right? They give you numbers and then they ask you not for a number, but they ask you for what is the identity of the halogen. How are you going to figure that out? Well, it turns out we can identify the halogen by molar mass, and we're going to do something similar to this in the lab. So normally if you want to find a molar mass, where do you go? You go to a periodic table and you can find the molar mass of all these things, but that will not help you identify it, right? So you need to find what I would call the experimental molar mass. So in this case, the molar mass is going to be grams divided by moles. That's what molar mass is. It's the ratio of grams to moles. Well, we can actually figure this out with the information in this question. The grams of this compound are easy because they tell us. The moles are not so easy, but not surprisingly, because it's in chapter 9, we can use the ideal gas law in order to find the moles of the gas. So, PV equals nRT. We're trying to solve for n, so I'm going to divide both sides by RT, divide by RT, and I find that n equals PV over RT. Note that I just switched them around. So PV over RT equals n equals PV over RT. That's the same thing. All right, so let's plug in. The pressure has to be in atmospheres. So I'm going to plug in the 1.41 atmospheres times the volume has to be in liters. So don't plug in 109 milliliters. Divide that by 1,000. 0.109 liters. R is 0.08206, and again that's liter atmospheres per mole K. And again, memorizing this or having it on some kind of formula sheet, I don't know, is basically telling you the units of all the other things, which is helpful. The temperature has to be in K, but this time it's actually given in K, so 398 K. All right, calculator trick. If you multiply these two together, then divide by this one, then divide by this one, it can save you a step in your calculator, depending on what kind of calculator you have and how you use it, but it can save you a step. All right, n in this case, so again, this times this, divide by this, then divide by this, n equals 0.0047058 moles. Okay, so of course you can also multiply these two together, then put these in parentheses and then divide by these two together in parentheses. That will work as well. All right, so now the molar mass is grams per mole. Again, the grams are easy. The grams are 0.334 grams because the problem told us that. The moles are the ones you just found, 0.0047058 moles. And when you do that, you get 70.98 grams per mole. Now, if you look on the periodic table, this is going to be closest to germanium, but germanium is not a halogen. You have to remember that halogens are group 7A elements, and they are diatomic. So each Cl is 35.45, so two of them is 70.9. Now you're a little bit off here because it's like 70.9 something. That's not 8, but it's close enough. All right, Cl2 is your answer here. Again, each chlorine, if you look on a periodic table, is 35.45, and you have two of them, so 2 times 35.45, which is 70.9. All right, it says determine the density of CO2 gas at STP. So there's a formula, density at STP, and we mentioned before that 1 mole of any gas at STP is 22.4 liters. This is standard temperature and pressure. The standard temperature is 0 degrees Celsius or 273 K, and the standard pressure is 1 atmosphere. So density generally is mass divided by volume. Well, what's the mass of 1 mole? It's the molar mass. And what is the volume of 1 mole at STP? It's 22.4 liters. So it leaves us with a new equation. Density at STP is the molar mass per 22.4 liters. So carbon 12.01 plus 2 oxygens, which are 16 each, gives you 44.01 grams of carbon dioxide. And at STP, it'll take up 22.4 liters, which gives you an ultimate density of 1.96 grams per liter. Note the density of water is about 1, right? You've learned that before in the lab. I think it's presented in the lecture as well. How is it possible that the density of carbon dioxide is 2? It's because the density of water is 1 gram per milliliter. This is 2 grams per liter. So the reason these densities are such large numbers, if you will, is because they're grams per liter, and a liter is 1,000 times more volume, of course, than a milliliter. So this is about 500 times less dense than water. But for this case, the answer is choice letter E. All right, so question 9 is a Dalton's law of partial pressures question. It says a mixture of 0.22 moles of carbon monoxide, 0.35 moles of hydrogen, and 0.64 moles of helium has a total pressure of 2.59 atmospheres. What is the pressure of hydrogen? Okay, so a couple things to point out here. I like to talk about air. Air is about 78% by moles nitrogen, and it's about 21% by moles oxygen. It's about 1% by moles argon, and less than 1% of everything else. These are not exact numbers, okay? So the air is theoretically exerting 1 atmosphere of pressure on you as you watch this question. Well, that means that 78% of the air pressure is coming from nitrogen molecules bouncing into you. Specifically, 0.78 atmospheres of pressure is from nitrogen bouncing into you. Oxygen is 21% of the air by moles, so about 0.21 atmospheres of the total 1 atmosphere of pressure is coming from oxygen. About 1% or 0.01 atmospheres is coming from argon, and then less than 1% for everything else. So that is basically how this works. So we call these mole fractions, but mole fractions are the same as percentages. We just don't multiply by 100. The mole fraction of nitrogen is 0.78. The mole fraction of oxygen is 0.21. They're just not multiplied by 100. So it says 78 and 21, they're 0.78 and 0.21. So that's basically all this is. So it looks like kind of fancy math, but it's really not. So let's look. Dalton's law of partial pressures tells us that the pressure of hydrogen, because that's what this one asks about, equals the mole fraction of hydrogen, a chi, times the total pressure. Okay, now a mole fraction and a percentage are the same thing, except a mole fraction or a fraction is out of 1 and a percentage is out of 100. So the mole fraction of hydrogen is going to be equal to the moles of hydrogen divided by the total number of moles, which in this case is the moles of carbon monoxide plus the moles of hydrogen plus the moles of helium. Because this particular sample of gas has carbon monoxide, hydrogen, and helium in it, so we need to add up all the moles. So the mole fraction of hydrogen is equal to the 0.350 moles divided by the carbon monoxide, which is 0.220 moles, plus the hydrogen, which is 0.350 moles, plus the helium, which is 0.640 moles, which again, I just got from right here. Okay, sorry, it's off the screen a little bit. Now, when you do the math, you find that the mole fraction of hydrogen is equal to 0.289256. Another way of saying this is it's about 28.9% hydrogen by moles, just like the air is about 78% nitrogen and 21% oxygen by moles. Well, let's look at the total pressure. In our example for the air, it was 1 total atmosphere. In this case, we have a higher pressure of 2.95 atmospheres. So we take the pressure of hydrogen by multiplying the mole fraction of hydrogen, that number is 0.289256, and multiplying it by the total pressure, which in this case is the 2.95 atmospheres. And when you do all that math, you find that the pressure of hydrogen is 0.853 atmospheres. The rest of the 2.95 atmospheres come from the carbon monoxide and from the helium, where helium is going to have the largest percentage because there's the most moles of it. Okay, but if you added them all up, they would add up to the 2.95 atmospheres. But in this case, to answer this question, it's choice letter B. All right, so number 10, we have a gas law stoichiometry problem. It says determine the volume of oxygen at STP formed when 50 grams of KClO3 decomposes according to the following reaction, and then it gives us the molar mass for KClO3. So if we look at this particular reaction here, what we need to know is that 1 mole of oxygen, or any gas, is going to have a volume of 22.4 liters at STP. Now it's just a stoichiometry problem. We're starting with grams of KClO3. If we could find the moles of oxygen, we could find the volume of oxygen. Specifically, we want to go from grams of KClO3 to moles of KClO3 to moles of oxygen, and then finally to grams of oxygen. No, we don't want grams of oxygen. We could find that. We want liters of oxygen, though. That's what it actually asks us for. All right, so now, starting with the 50 grams of KClO3, as we've done before, we're going to use the molar mass to convert it to moles. So I'm going to put the 122.55 grams of KClO3 on the bottom, and the 1 mole of KClO3 on the top. Conveniently, it gave us the molar mass in the question. Now, I'm going to convert from moles of KClO3 to moles of oxygen. As you've done before, use the balanced chemical equation. In this case, we're going to put 2 moles of KClO3 on the bottom, and according to the balanced chemical equation, 2 moles of KClO3 forms 3 moles of oxygen. We're now going to convert to liters of oxygen using this new information from the gas law chapter, which is 22.4 liters of oxygen is equal to 1 mole of oxygen. When you do all of this math, multiply by the top, divide by the bottom, you get 13.7 liters of oxygen, which is choice letter D. All right, number 11 says, which of the gases on the graph below has the largest molar mass? Okay, so when you get a graph, the first thing you want to do is, of course, read the axis. So this is molecular speed, all right, and this is number of particles. Okay, so basically, you can see 2 things from this graph. Let's compare D to A because they're at the extremes. For D, you could see that the top of the graph, which is technically not the average, sometimes I call this as the average, this is the mean squared speed, but this is effectively the most common speed for D is here. And if you look here, this is about, I don't know, 400-ish meters per second is the most common speed. If you look at A, the most common speed somewhere around there, somewhere around maybe 1050 meters per second, something like that. Okay, so this is the most common speed for A. So what you could see is the A molecules most of the time are moving a heck of a lot faster than the D molecules. There's another thing to notice here, which is the range of speeds for the A molecules is much greater than for the D molecules. You'll notice that for the A's, there are some going over 2,000 meters a second. For the D's, there's basically none going over 2,000 meters per second. So A has a much greater range of speeds. It also has a much greater, not technically average, but most common speed. Now, we need to decide which gas has the largest molar mass. Well, the one with the larger molar mass is moving slower. The reason that all gases occupy 22.4 liters at STP is because the larger molecules are moving slower. The larger molecules, which on average are moving slower, are exerting the same force on the walls of the container as the smaller molecules moving much faster. This is similar to if you were to look at a crash test. If you were to take a big truck and crash it into the wall, if you wanted to take a compact car and crash it into the wall with the same force, the compact car would have to be moving much more slowly because the compact car has much less mass. So the large gas molecules are moving more slowly, and the small gas molecules are moving much quicker, such that they can still both exert the same amount of pressure or force on the walls of the container. So here we have choice letter D. So if you didn't see the previous video, that would be a good place to start. It says which best explains why xenon and helium exert the same pressure on a container under the same conditions. So the same number of moles, temperature, and volume. All right, so why did the two molecules exert the same amount of pressure? So if you look at this, all right, relatively speaking, helium is this big and has a mass that's around 4. And xenon, relatively speaking, is much larger. I'm not sure that that's the right proportionality, but that's okay, and has a much higher molar mass that I don't happen to know off the top of my head, but it's much larger and much more massive. However, if you have the same number of these at the same temperature and volume, they'll exert the exact same pressure. Why is that? It's because the helium molecules are moving much faster on average than the xenon molecules. So the xenon molecules move far slower on average than the helium molecules. So therefore, when they hit the sides of the container, this one's moving slower and exerts the same amount of force. Like in the previous example, this would be like the big truck, and this would be the much faster moving small car. Note that these first two answers are ridiculous. There are more helium molecules in the container than xenon molecules because it's lighter or smaller. That's the only difference between these two. But I already told you there's the same number of moles. So if there's the same number of moles, there's the same number of molecules. And this one is just the backwards answer. The xenon molecules are moving far slower, not far faster than the much smaller helium molecules. So again, these move slow and these move fast. Number 13 says, which best explains why the pressure of a gas isn't ideal? So, gases are not perfectly ideal. Some are very close, okay? If gases are at very high temperatures, they tend to be pretty ideal as long as they're not under extreme pressures. They also tend to be pretty ideal if they're very small. So helium is one of the more ideal gases, but they're not perfectly ideal, okay? So they can be very close to ideal though. So let's look at the answers. It says the ideal gas law incorrectly assumes that gas molecules are moving. No, it's correct to assume that gas molecules are moving. Any molecule above absolute zero is moving. The molecules in the table or whatever hard surface you're near are moving because it's not above absolute zero, or excuse me, it is above absolute zero where you are. So the molecules in this table right here are moving because it's above absolute zero. The ideal gas law incorrectly assumes perfectly elastic conditions. This is correct, okay? In real life, gas molecules tend to stick together. Larger molecules tend to stick together more than smaller ones, as you'll learn in the next chapter on intermolecular forces. Additionally, if you have lower temperatures, the collisions tend to be less elastic and there are more of these intermolecular forces. The ideal gas law incorrectly assumes that there's empty space between gas molecules. Gases are mostly empty space. In fact, a correction for the volume is that the ideal gas law assumes that it's all empty space and the molecules themselves don't take up any space, but the molecules themselves do take up space, and at high pressure, the volume of the molecules plays a larger role. And it says all gases behave ideally under all conditions. That is simply not true. Okay, so the answer here is choice letter B, and it's basically looking at the van der Waals equation through a question like this. So I appreciate you watching this video. I again want to give you the disclaimer that Jesse and I made this practice set. The instructors had no say in this. Jesse and I don't go to class, so we don't know the classroom examples. Don't use this as the only thing to study, and don't assume every problem here will be on the test, or that every problem on the test is on here. You could get completely different questions on the test. Again, there's a disconnect here because we don't, you know, we don't do the lecture and they don't make this practice test. So that's our disclaimer. Thanks for watching, and keep working hard.